right, chapter 4, it's all about carbon. Got like 92 naturally occurring elements or something close to that. And biology is really focused on carbon. It's focused on water too, but water's not an element. So most of our dry mass or dry weight has a lot of carbon in it. And carbon is a great element for life for many reasons. So here you've got kind of a molecule with carbon. It looks like it's got some hydrogens and some other random atoms maybe attached to it. But, on its own, it actually forms the shape called a tetrahedral or tetrahedron. And because of carbon's ability to make bonds, four bonds, they can actually form a number of different shapes. And here's one of them. So organic chemistry, you may have heard of it. That might be one of your prereqs. This is a study of like carbon compounds. And usually they don't study stuff like carbon dioxide. Usually it's hydrocarbons. And chapter 4 is just a brief primer on this. So carbon can form, like I said, lots of different types of shapes of molecules because it can form four bonds. But it also can actually bond with a lot of different molecules. A lot of different elements. So nitrogen, oxygen, other carbons, hydrogen, phosphorus, sulfur. And that gives carbon kind of unique chemical properties along with unique shapes. So this is a review. This is just saying it can form four bonds. It can make large, complex molecules. And the reason why it can do that is carbon makes very strong bonds with itself. Makes a tetrahedron if it is only forming four single bonds. So when you make these molecules, if you have kind of one carbon, we call that methane. If you bind two carbons together, it's called ethane or ethane. And if you form a double bond in between, we call it ethene. And the whole study of organic chemistry, they do this. This is not really within our scope to kind of go over like every single one of these. Some of you might enjoy it. Some of you might loathe it. I will say, though, pay special attention to methane, because methane will come up later on in this chapter, and you'll see it a lot. We'll call it like a methyl group, and that's CH3. But what this slide is really showing is numbers of ways in which we can represent these molecules. So we've got the molecular formula right here, just CH4. And then we got the structural formula. If you were writing it out in 2 dimensions, kind of flattened, like almost on a plane. But and that kind of shows us the arrangement. But that's not necessarily satisfying because these molecules aren't in 3 dimensions. So we've got the ball and stick model, which is just taking that structural formula and kind of like putting it out in 3 dimensions. And then the space-filling model, which kind of fills in like the electron clouds and shows you kind of the areas where everything is at. But you can see so ethane structurally, look at the structural formula versus ethene, they look very similar, right? But then if you look at the ball and stick, if you look at it in 3 dimensions, ethane is really just like if you were to take 2 tetrahedrons and kind of put them next to each other, that's what it looks like. But ethene is this planar molecule that is flat. So it is important to kind of think about 3-dimensional shapes of these molecules, and I think that's probably one of the more underrated things that should be emphasized, because sometimes these shapes, while they may not seem so important, end up having like major consequences, and I will try to emphasize it as we go along. So this is just kind of showing some of the elements, and we haven't really kind of gotten into the nitty gritty of the electron cloud, but this is showing the electron cloud for hydrogen, oxygen, nitrogen, and carbon, and they're focusing mainly on the valence number, which is the electrons kind of in the outermost area. And the reason why I pay attention to those is that the element or the atoms will bond, use those to bond. So here's carbon dioxide, and we can see another kind of representation where carbon dioxide has two double bonds, and here you can see like we're sharing two pairs of electrons each, two pairs here, making double bonds. Here's another urea. So there is a lot of diversity in like organic compounds due to variations just in the skeleton. So we have these things. I'm sorry, not yet. So here we can change like the length. We can have 3 carbons, 2 carbons, 5 carbons, 4 carbons. We can move like the double bonds around. So if you have something with a double bond, you can just move it around, and that's going to change the shape and potentially how that molecule kind of acts. We can branch kind of the molecules. So here is something called butane and isobutane, and we just took a methyl off of here and just put it in the middle. Now, if you were to look at the molecular formula, these two are the same, but you just kind of move things around. You still have butane, but in a different form. And then sometimes we can make rings, and that will kind of change. So we have cyclohexane and benzene. Both are rings. You see some ringed forms in amino acids, sugars, so on. All right, so this is just kind of a review. So when you hear this term hydrocarbon, it just means that like a molecule has hydrogen, i.e. hydro, and carbon, or carbon. So a lot of H's and C's, and then we're going to end up putting a number of different things. A lot of times oxygen gets thrown on there, sometimes sulfur, sometimes phosphorus, sometimes nitrogen. But hydrocarbons in general have a lot of like stored energy in them. So carbohydrates, sugars, and then like fatty acids all kind of have a lot of energy in here. So you can see an adipose cell, which is a lot of people call them fat cells. I don't really like that term, but whatever. Anyways, we have an adipose cell, and then that stores, this is called, like the technical term is a triglyceride. And then each kind of leg on this molecule is what's called a fatty acid. These have a lot of energy, and you can take this and you can break apart these bonds in a triglyceride, and you can release a lot of energy. So inside of all these cells here, we have lots of energy. Anyway, we have these things called isomers that are the same kind of formula but have different structures, and ultimately will have different properties. So we just mentioned butane, isobutane. So here we have another structural isomer with pentane, and then you just move the branch and you have methyl butane. So we can have what's called cis and trans isomers. So you'll have this on a double bonded kind of molecule with the carbon. So if you have two things that are on the same side, it's called a cis isomer, and then if they're opposites, it's a trans isomer. And then enantiomers, where we kind of have left and right-handedness, kind of mirror imagery. I don't go into this very much. I'm not very good at this, but I think you should also be familiar with this. So these two are mirror images of each other, even though they're the same molecule, but they can act very different, possibly. So we do have some kind of drugs that are enantiomers of each other, ibuprofen and albuterol. So ibuprofen reduces pain and inflammation. You have two enantiomers. One is effective, so the S-ibuprofen is effective, and then R-ibuprofen is not effective. So whatever it's acting on, for that shape, it doesn't fit in there. And then albuterol is a an asthma medicine, and like usually an inhaler. Same thing. You have one form which is effective and another that is not effective. And once again, shape is important. Even though these are pretty much the same shape, they're mirror images. One works, the other one doesn't because of whatever is receiving that signal. Whoops.